Hi, I'm Doc Palmer. I'm the author of McGraw-Hill's Maintenance Planning and Scheduling Handbook. Because the concepts of planning and scheduling are a bit unusual, they're a little bit hard to master. But they're fairly simple. We just need to run planning as a Deming cycle, and we want to fully load schedules to defeat Parkinson's law. This is the third session we've been doing on maintenance planning work order codes. And today we want to talk about failure, cause, and action codes. We want to know where we need to spend money. We have thousands and thousands and thousands and thousands and thousands of work orders in our history. These work orders help us analyze where our biggest opportunities are. Well, our biggest problem is the waterfront at Northside Generating Station. It's the cathodic protection system during the spring, but actually not cathodic protection, it's the electrical system supporting that. How would you know that without work orders? And how would you know that without analyzing those work orders? There's a huge opportunity to do projects and spend your money to save money later. For proactive maintenance, the ratio is 1 to 10. That's not Doc Palmer's number, it's the industry number. Every extra dollar you spend on proactive maintenance, like greasing a pump correctly, saves you $10 on the bottom line from replacing a bearing, collateral damage, and loss of product. But the industry number for a project is 1 to 100. Every extra dollar you spend purchasing, engineering, correcting a situation at your plant with a project saves you $100 on the bottom line. Instead of having to grease it continually, maybe there's a better system that doesn't even require that. You're avoiding some of the proactive maintenance, and you're avoiding the reactive maintenance by you're putting in a more robust system. But where do you find that project opportunity? How do you rank your projects to know where you should spend that money? That's in these failure, cause, and action codes. Most people make them way too complicated and hard to use. At our plant, we gave each craftsperson a laminated legal sheet of 200 possible failure codes. And the idea was they were supposed to pick a code at the end of a job and write that. But nobody was going to scan through 200 different codes. So everybody had a top 10, and everybody had a different top 10. So it was just a worthless way to do things. You've got to keep those to a minimum. A pump can fail in about 100 different ways. But there's probably, 6 or 7 most common ways. So I would keep it, maybe 7 or 8 most common ways a pump can fail, and then put other. Don't make them pick one of the other 92 ways, which rarely ever happens. But don't make them pick one of the 7 or 8 if that's not what happened. So have here's the ways a pump could fail. Here's 8 ways, and then other. And it's got to be, as we're going more and more electronic, they're not going to scroll. People are not going to scroll. But we're not going to scroll, include myself in that. We're not going to go to multiple pages. It's got to be without scrolling. So here's the 8 ways and an other. And just the Pareto analysis, maybe you ought to look at all those others after a while. Maybe go to 9 most common ways. But don't start off with giving them all 100 ways a pump can fail. And then we want to make everyone consistent when they're finishing a work order to click a code. So have PM also. So it'd be here the 8 ways a pump can fail. It's not those pick other or could pick PM. And then most systems, electronic systems, they want you to pick one code. Why did something fail? Well, it was this reason. Well, it could be multiple things. Mark Galley of Think Reliability in Houston teaches a great cause mapping, or some people call it root cause He shows this example of a person's walking carrying some boxes and they trip. Did they trip because they were carrying boxes where they couldn't see? Well, yes. Or did they trip because there was an obstruction on the walkway? Well, yes. Or did they trip because your process required you from carrying boxes over here to over there? Well, yes. Well, what's the root cause? Well, but there were three causes. And we want to identify all those and pick the one that's most practical to pick. Now, fixing this is a human issue, and human issues are difficult to fix. Now, we could remove the obstruction. That's an engineering fix, and it might cost $10,000 to reroute that obstruction. Or maybe for $500, we could change our process from carrying boxes from here to there, okay, from here to over there for $500. So what we would do is look at each instance and pick the appropriate thing that would fix everything. Then we don't have to spend the engineering or fix people or try to fix people. So there's not just one thing. Well, why did that fail? Well, there was a lot of corrosion there, but it was an electrical problem also. And you know, it does happen. The operator operated it incorrectly. Or just, this could be three things or three or four things. So let them pick all the things. And then throughout your system, what's your biggest problem? Looks like our biggest problem has to do with electrical work. Or our biggest problem is corrosion, even though there's a lot of Venn diagrams overlapping and stuff. So we're not just picking one code. And then we're also not preempting the remarks text. A lot of these systems, I think, were implemented, you know, speed. We want speed. We want people off their keyboards and doing work. But it's not as easy as just picking a code. There was this Jester's convention that this whole thing reminds me of. This reporter went to cover this convention, and the reporter walked in the room standing next to somebody. And somebody got up on the podium and said, 37. And everybody laughed. And somebody else got up and said, 46. And everybody was laughing. Then he went on and said, 146. Oh, and they were really laughing and rolling around. And this reporter nudged the guy next to him and said, hey, what's going on? What's going on? Well, oh, you're new here. Well, this is a Jester's convention. We're all professional comedians, and all these jokes are as old as the hills, and they've been passed down from grandfathers to fathers to sons. And we know all the jokes. We just like getting together. So just to save time, we've just numbered all the jokes. Well, that's pretty interesting. And somebody gets up and says, 6,004. And everybody's laughing and laughing. And then somebody gets up and says, 206. And we go, oh, boo, 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 boo. What happened? What happened? Well, he messed up the punchline. And so it's just, you just can't condense everything to a number. What happened over there? 46. What are you going to do about it? We're going to do a 37. What are you going to do about that one? Oh, that one was a 23. It's just, that's not the purpose of these codes, is to reduce mechanic feedback time. It's to allow reliability engineers to take massive and thousands and thousands and thousands of work orders and get it down to, look, this 500 work orders here seems to be a common problem. And then that poor reliability engineer or somebody with that function needs to read those and see what's going on and see where we can spend some money, maybe develop a project and implement a change and spend some money in the right place. Remember that the industry number is 1 to 100. Every dollar you spend in a better engineering, better purchasing project to make something more inherently more reliable saves you $100 on your bottom line, producing your product and making a profit. So that's why we do this. Now, we've got to, this is an advanced practice. You're probably doing a decent job overall. You're keeping things from breaking because you're doing more proactive work than a normal company. But we want to get to absolutely the pinnacle of reliability. And these codes are an advanced practice to do that. We hate to give our mechanics, electrician, instrument techs, operators one more thing to do. This is an advanced practice, though. Make it easy. Don't make them scroll through a bunch of things. Make it easy to pick something. Don't limit them to just pick one thing. Don't force them to pick something not appropriate. There's a lot of ways you can make this easier. So you've got to let the techs, your craftspersons, know why we're doing this. We're trying to decide where we can spend the most money. Well, I can tell you what we need to do. Well, yeah, but data is important. That's what this data is for, a data-driven organization. I think planners should be able to have super rights to your CMMS and be able to correct some of these codes. I'll be reading a remarks description about a big electrical problem. And they checked corrosion, but they didn't check the electrical code. Or I'll read a big thing about how this happened, this happened, this happened. And I think they could have picked one or two more codes to make it helpful with the big thing. So I know we need to close down the system at some point so we don't ruin our history or change our history. But I think planners need some rights when they're closing these, and probably some reliability engineers too when they're looking through the data and reading remarks and stuff to correct our database. Now, the final question though, will the techs use them? What should planners be doing about it? Is, will reliability engineers use this information? Well, it's an advanced practice, and we should be using it. But there's a chicken and an egg situation here too. If we, as far as the planning department, maintenance department, are not collecting these codes, the reliability engineers can't use them. They need to help us set us up with the right codes in our system so it's easy to use. Huge value from this, absolutely huge value. So, well, thanks. That's my opinion on that. That's my 2 cents. Thanks for being part of my maintenance family today. And you can see more information on codes and other things I think about planning and scheduling in my handbook, also my website, palmerplanning.com. But thank you for having me, and we'll see you next time, and God bless.